Okay, hello everyone. So today we'll be discussing section 4.7, which is Mohr circle representation of a general state of stress. Meaning, when you do not have a plane stress assumption and then you have all the 6 components of stress, what would be the Mohr circle representation for that? So, a word of warning, this particular topic is it won't be dealt in with the same rigor as the earlier ones. The reason being the mathematics of this topic is slightly more complicated, and hence this topic is normally reserved for advanced course, say a linear elasticity course or advanced mechanics of solid, some course like that. But we are doing it over here just to get a physical understanding of what would happen when you don't have a plane stress condition. Okay, so that's the motivation to go into it. So let's see how we can get around this. So as the authors in your textbook say, thus far we have concerned ourselves with the problem of plane stress and have limited ourselves to transformation of axis within that plane. So we have seen that, okay, if the coordinate systems rotates by an angle theta, in the Mohr circle you have a rotation of 2 theta. Okay, so that's how that used to happen there. Now suppose we now consider a situation in which the stress components associated with the z-axis are not zero. Okay, so tau zx, tau zy, and sigma z, I'm sorry, not equal. So these are not equal to 0, so that it is not plane stress. Okay, because in the plane stress, if you remember, all the z components of stress, all the stress components which had a z in them were 0, and we had seen this in the earlier classes. That is a situation in which the state of stress may be said to be perfectly general. So in this case, I mean, your this 9 by 9 stress components usually can be written as a 2 by 2 for plane stress. Okay, and the reason for that is anything with a z is 0. Now this is what we want to do in this section, study the transformation of this using Mohr circle. Okay, now further let us suppose that we again wish to find the stress components associated with the plane whose normal x dash lies in the xy plane and makes an angle theta with the x-axis. So you now have a 3D situation in which at a particular point, okay, you have the 1 2 3 1 2 3 1 2 3, this 9 by 9 system defined, and you want to now find what this will be if you rotate the existing coordinate system. Say this x dash becomes, and this rotation has happened along by the angle theta. So this was your original x, this was your y. Okay, the only thing is that right now you have all the 6 components of stress. Okay, so if we cut out a small wedge similar to that of figure 4.15, now we want to cut out a small wedge similar to 4.15. Let's see what 4.15 was. Okay, a small wedge like this. Okay, we will cut out a small wedge like this, and let's see how that and the only difference over here will be that you do not have z components. For example, you do not have tau zx, you do not have tau zy. Okay, in our case we will take that. So let's see how that is done. So if we cut out a small wedge similar to figure 4.15, we find that the stress components acting on the wedge are as shown in figure 4.21. So let's first of all check whether everything is all right. So this is for the plane which is Pn and delta z. So you will have a sigma y, that is correct. You will have a tau yz, that is correct. You have a tau yx. Okay, that is correct. So this is tau yx according to our convention, but also tau xy because of the reasons you already are aware of. Let's now look at the plane PM and PN, okay, meaning this front face. So okay, so you have sigma z, correct, then you have tau zx and tau zy, okay, so this is correct. Now let's take the plane MP and delta z, okay, MP and delta z, meaning this vertical plane. It will have a sigma x, it should have a tau xy, it should have a tau xz. So this is tau xz, okay. Now let's take the plane which is behind, okay, which is this plane, okay, vertically, this particular plane which is behind, okay. For that it's shown by the dashed line. Okay, so I think this should be sigma z, so please make a correction of this in your textbook. And then the rest of the components are tau zy, okay, and tau zx. So this is correct. Only one correction is there. This you can make in your textbook. Do it as well. Okay. Now let's now look at the inclined plane. So at this inclined plane, so this is that axis x dash which is rotated by an angle theta from the original x-axis. So you want to write now, write the components as sigma x dash in this new system. It will be tau x dash z, okay, tau x dash y dash. So notice that z dash is the same at z. That's why you do not have a tau z dash x dash over here. Okay, so tau, because the z axis is not rotated, so that's why you have a tau z x dash, and here you have a tau x dash y dash. Okay, so as we have seen, the difference between this figure and figure 4.15 is that you have these z components of stress littered around. Okay, these were not there in your previous case because it was a plane stress situation. Okay, so we note that in addition to the components sigma x dash and tau x dash y dash on the plus x dash face, so this, let's just call it as plus x dash face. Okay, so in addition to that, we will also have a shear stress which is tau x dash z. Okay, so this is that one. Okay, so once this is done, now we want to examine figure 4.21. So remember, this is a small wedge which has been cut from a body in a general state of stress. It's not the whole body itself, just like it was not in the figure 4.15 as well. Okay, so when we examine figure 4.21, we see that the stress components sigma x dash and tau x dash y dash are unaffected by the stress components associated with the z axis. Let's see. So what they say is that sigma x dash and tau x dash y dash are unaffected by sigma z tau z. by, let's say, all stress components with z-axis. This is the claim which the authors make, that sigma zx dash and tau x dash y dash are unaffected by all components of stress associated with the z-axis. This results from the fact that for force equilibrium in the x dash and y dash directions, the contributions of the components tau zx and tau yz acting on the plus z face of the wedge are exactly balanced by those components tau zx and tau yz acting on the minus z phase. So this results from the fact that the force equilibrium in the x dash, so let's see the force equilibrium in the f, okay, x dash direction, and also force equilibrium in the, so this should be 0 in the y dash direction. The contribution of the components tau zx. So if you want to consider the contribution of I think it should be, okay, so tau zx, let's see whether we can understand tau zx. Okay, this is tau zx, so we are referring to this one. Okay, so we want to now see the contribution of this stress components tau zx in this x dash direction. So essentially your x dash is something like this, x is something like this, and clearly tau zx is something like this. Okay, now when you want to consider the contribution of this stress, you have to multiply it by a suitable area, which is say mp and pn. Okay, let me write it nicely, mp and pn, that becomes a force now in this direction, and then you have to resolve this particular force in this direction x dash. Okay, so you have to resolve it like this. Now this is one part of it. Let's look at the other force tau zx over there. Okay, this one will have tau zx acting in this direction. Okay, and that will be multiplied by the area of this plane, which is the same as area of this plane. Okay, so that would be tau zx multiplied by, sorry, mp into pn. Now this is what they say, in trying to do this, this is equal and opposite, and hence they will, the tau zx component will not contribute anything to this equation. Okay, now consider the second case. In this case you have a tau yz that will give you a force, so this is y dash. Okay, so you will have a tau yz into area. Similarly you will have this tau yz into area, which is equal and opposite, so they will have zero contributions as a resultant because they are equal and opposite. So that explains, and so even if you resolve this across to the y dash direction, just like you have resolved this x into this x dash, or project this force on this, so project this on this, it will still be zero. So that is what they say, that the force contributions in the x dash and the y dash directions of the components tau zx and tau yz acting on the plus z phase, this is a plus z phase, and on the minus z phase, this is a minus z phase, are exactly balanced. And that is why you say that the stress components sigma x dash, okay, so sigma x dash and tau x dash y dash are unaffected. And how do you know sigma x dash? Sigma x dash is essentially just sigma x dash equal to this force which you have. Okay, so this particular force divided by the area, and similarly tau x dash y dash is essentially this particular force divided by this inclined plane area. So that's where this is coming from. Okay, just to clarify again, it is not that tau zx and tau yz are not acting or they have to be zero. No, they are allowed to be non-zero, but they will not contribute in these two stress components. We have seen the reason for that. So let me just remove this now. I'll keep the statement up, okay, but I'll remove this reasoning. Of course, it will be recorded, so you are free to go back and check it. Okay, now if we now consider the force equilibrium in the z direction for the wedges, because z and z dash is the same direction even after rotation, nothing has happened to the z axis. So z in the z direction you want to apply the equilibrium, force equilibrium. So let's start from one end. What we'll do is we'll just have the stress multiplied by the area. So in the z direction, so summation of all the forces in the z direction must be 0. So for that, let's start with the inclined plane first. So this would have this component contributing, so that would be tau zx dash into what is the area, mn multiplied by delta z. This is delta z. Okay, what's the next one? You will have this sigma z, that would be sigma z multiplied by area. The area is np into mp divided by 2, half into base into height. Now you will also have a tau xz, so let's see where that happens. This one. Okay, but since it's acting in that direction, you will have a negative sign. So tau zx into mp into delta z. Okay, let's have the tau yz, that would be minus of tau yz into pn or np. Let's just into delta z minus, then you have this sigma z, so sigma z into np by 2 is equal to 0. So this is how the force equilibrium in the z direction can be written. Just confirm whether all this makes sense to you and whether nothing has been left out. Okay. Now when the trigonometric relations between the sides MP, NP and MN are used, what is the trigonometric relation between NP, MP and MN? Okay, so it seems this angle is theta, okay, as is given. So this angle is 90 minus theta, this angle is 90 minus theta, this is 90, this is becoming theta. So what is the relationship between all these things? Let's see. So we want to now divide by something. It's always better to divide by mn. See, let's see how we can arrive at the next equation. So the next equation is tau zx dash equal to tau zx cos theta plus tau yz sin theta. So I think the best way is to divide both sides by m bar mn delta z. Okay, so first thing, I think this gets cancelled with this because they are equal. So in this case now you can write tau zx dash, so dividing both sides by mn delta z, because it's a non-zero quantity. You have to mention that you can only divide it when it's a non-zero quantity. So then you get tau zx mp by mn delta z by delta z is 1 plus tau yz np by mn. Okay, so cos theta is equal to b by h, so mp by mn. So this becomes tau zx cos theta plus tau yz, and np would be, I think, sin theta, np by mn, so this is sin theta. Okay, so we arrive hence at this equation, which is 4.30 in your textbook. Okay, so what I'll do now is I'll just write this equation over here. So tau zx dash is equal to tau zx cos theta plus tau yz sin theta. I'll just rub these things. .30. Okay, so if we resolve the stress components tau zx and tau yz on the plus z face, so we are talking about tau zx and tau yz on the plus z face, so this is the plus z face, into components perpendicular and parallel to mn. So let's see, you have tau zx into area, so I am writing it like a force with a magnitude and the direction. I do not want to say that we are resolving the stress component, okay, because stress component is a scalar quantity. So that's why I am showing it by a force, okay, tau zx into area, and you want to now resolve this into a direction which is perpendicular and parallel to mn. So mn is like this, so this is perpendicular to mn, this is parallel to mn. So I'll just write tau zx into a mn parallel, this is tau zx, sorry, tau zx mn perpendicular. Okay, similarly you want to say tau yz, where is tau yz? It's in this direction. Okay, so I'll just multiply it by area. So this is tau yz into area into mn perpendicular. The second is I guess this tau yz into area mn parallel. Okay, Okay, so as you know, the direction which is perpendicular to MN, I mean this one and this one, this makes an angle of theta with the x-axis. So this is an angle, makes an angle theta. This is the angle theta. Okay, and fine. So let's see. So if you want to find the value of this thing, you have to project this force over there. Okay, so this will be equal to tau zx a cos theta. Always a projection. Okay, tau zx. So your triangle will actually be forming like this. I think you already know all this, but that's how your triangle will form. Okay, that's the first part. Now let's try to write this particular thing, tau y z a m n perpendicular. So this particular angle will be pi by 2 minus theta. So if you want to project this tau yz on this direction, you will have to take a tau yz. So this will be equal to tau yz a into cos of 90 minus theta, and that is tau yz a sin theta. Okay, okay, so this term appears over here and this term appears over here. So if we read the text which is in your textbook, if we resolve the stress components tau zx and tau yz on the plus face into components perpendicular and parallel to Mn, we find that the right hand side of 4.30 is the sum of the components perpendicular to Mn. So this is the, so A goes off because A is divided over here as well. Okay, so this is the component of tau zx along a direction which is perpendicular to Mn. This is the component of tau yz along a direction which is perpendicular to Mn. Okay, so this is the summation of those two. Thus we see that tau zx dash is of such magnitude as to be equal to the shear stress component acting on the plus z face in the direction perpendicular to Mn. So tau zx, with this you can see that tau zx dash, the magnitude of this tau zx dash, let's look at what tau zx dash is, this one. Okay, so tau zx bar is of such magnitude as to be equal to the shear stress components acting on this plus z face in a direction which is perpendicular to Mn. Okay, this is something which you must note right now, that how does this new tau zx bar depend on the things which you already know. Okay, so that's something which we have shown. Let's keep it there. So as a consequence of our, so as a consequence of our investigation of the general state of stress, remember this general state of stress which we had over at the start, we may conclude two things based on these things which we have just observed. So the first point is that the results given by equation 4.25. Now can we see equation 4.25? Please check in your textbook. Equation 4.25. Okay. equation 4.25. So this has a sigma x dash, tau x dash, y dash, and sigma y dash. Okay. So the results given by equation 4.25 and the Morse circle representation of these, which we have seen in the earlier section, are correct whether or not the stress components sigma z, tau yz, and tau zx are 0. Okay, so you have these components, I mean the expressions which you had would be valid even when tau zx, tau zy, and sigma z are not equal to 0. So when they are 0, there it is anyways there, and when it's not 0, this will be true. That's the first one. And the second one is that if either of tau yz or tau xz are non-zero, then in general there will exist a shear stress component tau zx bar in the x dash phase, this one. Okay, so you see over here, if any of these two terms are non-zero, then this would imply that tau zx dash is non-zero. Okay, so this tau zx bar, tau zx dash will exist on the x dash phase in addition to this tau x dash y dash. In such a case, the 1-2 axis of figure 4.19, this one, the 1-2 axis of 4.19. First of all, how is this Morse circle coming? The Morse circle is coming because equation 4.25 was valid even when the other shear stress components are, the z stress components are non-zero. So you would get the same Morse circle. Okay. Now, since tau zx dash will not actually be equal to 0 when one of them is not 0, which is the case in a general state of stress, then in such a case, the 1-2 axis, this particular axis, should not be called as the principal axis of stress for the normal to a face on which no shear stress component acts. The reason is we don't want to call it a principal axis because there is a shear stress acting, right? Tau zx dash is a shear stress. So 1-2 cannot be called as a principal axis of stress. Okay, since for principal axis of stress you should not have a shear stress component, but here you will see that tau zx dash will be there as a non-zero quantity. So you cannot call 1-2 as a principal stress. Okay, so that's the first that's the second part, second equation as well. So these are the two observations. Now let's the first equation, first conclusion is that 4.2 is valid even when this is not 0. Now can you check from what we have learned about this section that why this should be true? The reason is because of this statement. It says that sigma x dash over here will be unaffected by the stress components associated with the z-axis. Okay, and hence and tau x dash y dash will also be unaffected by the stress components associated with z axis. And the same can be said for y as well. So you can just have a 90-degree rotation and you can say the same over there. That is why 1 is true. This first conclusion is true. Okay. So that's the reason why this, and we have seen how this has come about. Okay. Not that those components are present absent, but their effect will be 0. So we have already seen how this statement is coming in. And if you have a doubt, please go back and check how this is coming in. Okay, so that's the so-called end of this first set of conclusions which we made, very important conclusions. And let's now move to the next part, which is we now consider further the case of a plane stress. Let's for a moment come back to plane stress. We now consider the case of plane stress and investigate the stress components referred to axes which do not lie in that plane. We begin by showing in figure 422a an element from the plate of figure 4.14. So let's go to figure 4.14. Figure 4.14. Okay, this is the figure 4.14, and you have taken an element out of this plate. Okay, so because it's a plane stress situation, that's why you have a thin plate. Okay, we have now come back to plane stress for a moment. Okay, so this is an element which has been taken out from that plate with faces of the element oriented to coincide with the principal stress directions 1 and 2. Okay, so the faces of the elements oriented to coincide with the principal stress directions 1 and 2. So what you have done is you have found out the state of stress, then you converted it to the principal stress system, and you realigned this element which you have along the principal directions. So that's why sigma 1 is like this, and sigma 2 is like this, and sigma 3 was anyways like this. So sigma 2 and sigma 1 are like in this opposite phase. So sigma 2 is on this phase, sigma 1 is on this phase, in the opposite direction, of course. Okay, so that's how this element has been aligned so as to coincide with the principal directions 1 and 2. The direction 3 is perpendicular to the 1 2 plane and thus is parallel to the z axis. So the direction 3 is parallel to the z axis. Okay, and this you already know because it's a plane stress situation, so nothing much will happen to 3. It will continue to be parallel to the z axis. Okay, consider all planes which can pass parallel to the 2 axis and so intersect the 1 3 plane. Let's see this. You want to consider consider all planes which can pass through which can pass past parallel to the 2 axis and so intersect the 1 3 plane. So you have this 1 3 plane, okay, and you want to have planes which are parallel to this axis. So I am drawing an inclined plane. See if it makes sense. So this is a plane like that. Okay, it will cut through the 1 2 plane. It is parallel to the 2 direction. Okay, and clearly it will have this intercept on the 3 axis, it will have this intercept on the 1 axis. Okay, so this is one of the planes, and you can have many other planes, infinite planes for that matter, which are like this. Okay, now the stress sigma 2 would have no influence on the stress components on these. So the stress sigma 2 will have no influence on the stress components on these planes. Okay, so the stress components in these planes would be, let's call it sigma ij, but it says this sigma 2 will not have any influence on it. How can we say that? Let's come back to this. Yes, so this plane over here is similar to this inclined plane over there, and this 2 axis is similar to the z or z dash axis over here, and that is why, just like in this particular case, the stresses sigma x dash, okay, sigma tau x dash or sigma y dash, they will not be influenced by your sigma z. Okay, you can see this, there is no effect on tau x dash y dash, on sigma x dash and sigma y dash if that need comes. There is no effect of all these 3 stress components on there is no effect on these components by sigma z. So similar thing is happening over here. So this inclined plane is this plane, this inclined plane is parallel to the z axis, this incline is parallel to the 2 axis. So that is how this statement is written, that the stress sigma 2 would have no influence on stress components of these planes. Okay, the stress components on one of these planes would depend only on the normal stress components along the 1 axis. The stress components on one of these planes would depend only on the normal stress components along the 1 axis. So sigma x dash, if you go to 4.25, so this plane is parallel to the 1 3 system. Okay, so at best any stress on this one, because it's a planar situation, so it will depend, it can depend on sigma 1 sigma 3, okay, and sigma 1 3 if you were referring to the general state of state. But in the principal system, sigma 1 3 is not equal to 0. Okay, so this any stress over here would depend only on either sigma 1 or sigma 3 or both. Okay, fine. Now sigma 3 is equal to 0 because it's a plane stress situation. Okay, so it would only depend on sigma 1. So we want to show this as a Morse circle. Sigma 3 is equal to 0. Okay, sigma 1 is a value which is not 0. Okay, and it's positive because we are in tension, and sigma 2 will not appear, at least when you draw this particular Morse circle. Okay, So sigma 2 will have no effect on any of this, any of the components on this particular plane. Now you can this was the this was, remember, the earlier circle for plane stress. We have discussed this in the last chapter, last section. So we are not discussing that over here. Okay. We are now discussing a situation in which this circle is drawn. Okay. Where sigma 1 is greater than sigma 2, which is greater than sigma 3, which is equal to 0. Okay. Now these are the two circles which have been drawn. Now consider finally you can obtain a third more circle which represents stress components on planes parallel to the one axis. So to draw this circle, draw a plane which is parallel to the one axis. Okay, and that will clearly intersect this 2-3 plane, and 2-3 plane is intersected, so you get over here. Okay, now I'll recapitulate this once more. In a plane stress, so what you have is you have a general three-dimensional state of stress. Okay, you have all 6 components. For a moment you take a case in which the you have a situation in which one direction, say sigma 3, okay, have a plane which is drawn parallel to sigma 3, and this is the situation which you had in your previous section. Okay, so the stresses on this particular plane will have two values, sigma 1 and sigma 2. So that is sigma 1 and sigma 2. Okay, there is nothing new in this particular case. Okay, and in this case clearly, I mean, the plane is parallel to the 3 axis. Then you have taken another case in which a plane is parallel to the 2 axis, and hence that would make intersect this 1-3 plane. So you would have 1 3 over here. Clearly 3 is 0 because it's a plane stress situation. Okay, and then you would have this plane which is parallel to the one axis, and that would make sort of cut or intersect this 2-3 plane. So you will have this sigma 2 and sigma 3. Now sigma 3 is 0, sigma 2 and sigma 1 are like this. So you have this set of 3 circles in front of you. Okay, so this is how the general Morse circle can be drawn. Okay, for general state of stress. So okay, now you can have other cases in which sigma 3 is actually 0 and sigma 2 is compressive, sigma 1 is tensile. In that case so this is something you should do. Coming to sigma figure C and D, and in other case sigma 1 and sigma 2, both of them are compressive, so the Morse circle will look like this. Okay, so you have to be able to interpret this case, and this is something, this is an assignment for you to repeat this entire analysis for these two situations. Okay, so an interesting fact illustrated by figure 4.22 is that plane stress does not mean that the stress components are 0 on all faces except those which contain the normal to the so-called plane of stress. In figure 4.22D, we show that in some case of the plane stress, the maximum shear stress at the point occurs in faces whose normal is inclined to 90 degrees. So this is the tau max. Okay, but it's, you see, it happens in the 2 3 system, meaning the plane is parallel to one axis. Okay, so that is what they say, that the maximum maximum shear stress occurs in a plane whose face occurs at a point on faces whose normal is inclined at 45 degree to the so-called plane of stress. So the plane of stress in this case, okay, is this, but you have a 45 degree inclination. So this plane which you see is 45 degree inclined, and that is why it shows a 90-degree inclination in your Morse circle. So this is the last sort of observation in this for a truly three-dimensional case. And now the last of the last part, which we have to sort of just finish off with a comment, is that returning again to a general state of stress, we assert without proof. So what I am saying next is without proof. Again, the reason is because it is normally dealt in advanced courses of linear elasticity. Linear elasticity, advanced solid mechanics, and courses like that, they will deal with all these things. We assert without proof that each point within a body, there are three mutually perpendicular planes. So we have not actually shown, but if you have this general three-dimensional state, there is an orientation, sigma 1, sigma 2, and sigma 3. So there are three mutually perpendicular directions along which you can have these values. The shear stresses will be 0. Three mutually perpendicular planes on which there are no shear stress components. The normals to these planes are called the principal axis of stress at that point. And so this is by some complicated rotation, again a combination of rotations essentially, and it gives you this, the system transforms into something like this. So figure 4.23a illustrates an element of which the principal axes are labeled 1 and 2 and 3. Okay, and in this example the 3 axis is assumed to be parallel to the z axis, and thus the axis 1 2 must lie in the xy plane. If the 6 stress components associated with any 3 mutually perpendicular faces are specified, okay, if all these are specified, it is possible to develop equations which are similar to 4.23. So you have an equation which is 4.23. If you look at, you will have a sigma x dash, sigma y dash, and so on. 4.25 essentially. Okay, 4.25 contains all. So you can, the idea is that you can have sigma x dash equal to something, sigma y dash equal to something, sigma z dash equal to something, tau x, there is no shear stress anyways. Okay, so that is possible, and if this is the principal system, then there will be no shear stresses. So you can have something like this, and it can be shown that the stress components for all possible planes are contained in the shaded area. So this is a situation which is like this, I am guessing. Okay, yes, both of them there, and the third one, the third principal stress is 0, but you can have the shear values. That's the important part. Okay, so it's not a, okay, now it can be shown, not shown in this course, that all possible values of the shear stress components must lie in this shaded area. So it will not lie, say, over here. So you will never have this particular point as a possibility. And what is this particular point? A particular normal and a particular shear stress on that plane. And shear stress in a definition like this is normally the average value. So this is equal to tau x dash y dash square plus tau z x dash whole square. Okay. So once you convert this to this, and the motivation remains the same. Now in a three-dimensional system, you can use your theories of failure which you learn in your designing course by using these values sigma 1, sigma 2, and sigma 3. Okay, so that's the end of this particular topic, and I think we'll continue with in the next chapter in your about the discussions on strain in your next class. Thank you.